This is it. You are watching history being made. The first ever landing on a comet. I'm Dan Riskin. I am in the most exciting place on the planet right now, the European Space Agency in Darmstadt, Germany. And this crowd is cheering because an incredible group of scientists just put a lander on the surface of a moving comet. Now, they made it look easy, but this mission and what it's about to do are groundbreaking.
Is it real? Are we there?
This is a big step for human civilization.
It could revolutionize everything.
Desperate to reveal life's origins.
They're a treasure chest with a view back in time.
A quest decades in the making.
It's one of the most difficult things you can try.
An epic adventure to chase down a dragon and ride on its back.
The cherry on the top is really the landing.
Touching down,
it's all down to Isaac Newton now.
Where no one has landed before.
We're moving in for the kiss.
But first, separation anxiety. 7 agonizing hours.
I don't have any fingernails. They're gone already.
We are on the Comet.
A comet, up close with unprecedented clarity.
We're making history here.
This is one for the record books.
We know the world is watching this mission.
Andrea Akamatsu, the flight director, a little bit the man of the hour here. Now, how are you feeling after that incredible landing event?
Well, now I feel exhausted, but I feel overexcited. I mean, it was a big success for all of us. I mean, we've done one of the most difficult, most challenging operations in space ever, and we have been successful. We have landed on the Comet. Now we have to determine exactly how the lander is doing, but we've been successful. We've done our job today.
Yeah, and not a small job. I mean, it launched 10 years ago. The last few weeks have been an absolute roller coaster, and the story continues to evolve.
Absolutely. Now we have just done a part of the mission. We've already done a large part of the mission, and there's even a larger part of the mission in front of us coming in the coming months and coming years. So there's much more to discover around this comet.
Well, we've certainly enjoyed following you on the journey so far, and we look forward to what's to come. Congratulations.
Thanks a lot.
This is where the journey began.
Greetings, everybody, wherever you may be. Welcome again to Kourou, the home of Ariane. The launcher, as you see, is on the pad. The clock is ticking. The panels are green. What could be better? Sit back and enjoy it.
3, 2, unité. Top. Allumage moteur Vulcain. Allumage confirmé. Top. Allumage EAP. Décollage.
A mission like Rosetta, of course, has been in planning for many, many years. More than 20.
Yeah, I have been on the mission since '85. A lot of people said, what you are doing there is crazy. It's too ambitious, we can't do it.
Well, I've spent now 17 years working on this project. This has been so far the backbone of my professional career.
I was there when Rosetta was launched. I was sitting in the first row of the control room. And normally you find a lot of surprises. Everything went extremely smoothly.
A mission to put a comet-chasing machine worth $2 billion into space to travel further than any mission before it in pursuit of a comet at the edge of the solar system.
It's really got facets from previous Cometary missions all added into one.
Not only a hope to get there, but to put a lander on the surface.
So you have the exploration, the fact that we're going to go and observe one of these so closely as we've never done before, the long journey that we've had to get there, and also the science at the end is easy to connect to everyday life.
It's intimately tied into our understanding of the origins of planets, the origins of solar systems. This one comet is an icy treasure chest which has been locked away for 4.6 billion years, containing information which could unlock the secrets of the birth of our solar system.
Designed to fly for more than a decade. Massive wings fold out, reaching for the sun's strength. Rosetta is on a 6.4 billion kilometer, 4 billion mile trek to a target called 67P, known to pass by Earth every 6.5 years.
It's a great adventure, of course, doing something as crazy as flying a probe out into deep space, lining up in such enormous precision with a moving, dynamic object, and then being able to grab a hold of it.
A team of top-notch pilots doing everything they can to make the journey smooth.
5 milli-degrees per second.
That's the one.
From the time Rosetta splashed into space, she's had to navigate through crowded cosmic lanes. As fast as she's moving, she'll never meet her target without a serious boost of speed.
We had to use gravitational flybys in the solar system to wind our orbit up to get out there.
Thanks to the gravity, and we transferred this energy from the planet onto the probe, and the probe was continuously accelerated.
Along the way, the team gets postcards, reminders she is out there.
The first highlight for me personally was looking back at Earth and finding landscapes, so Africa, Europe, city lights at night. Then we swung by and had a very nice look at Mars.
Then they catch a miraculous up-close look at 2 rarely seen asteroids.
Wow, this was cool. It looks like a diamond in the sky. The fun part is these are high-speed flybys. So it just whoosh and you are flyby.
A trip of a lifetime. But the spacecraft is getting too far from the sun to maintain power. Putting the probe into a deep sleep will ensure it has the reserves for what it needs to accomplish later. A gutsy call has to be made.
We had to switch off most of the systems.
It was a tricky moment after such a long time. Just flip the switch, turn it off, and hope for the best.
We tried to challenge this hibernation mode because we consider it extremely risky.
A horrible thing to do for an operator. You want to be in contact with your baby, with your spacecraft, and you know you're not going to see it for 2.5 years. But you think of all the possible things that could happen in this period.
Waiting for the wake-up? Almost unbearable.
We had a predicted time, and we had some uncertainty. The tension grows very, very rapidly.
This was a totally different feeling. Extremely exciting on one side and worrying on the other side.
Am I crazy? I haven't heard from this spacecraft for 2.5 years. It's out there, hundreds of millions of kilometers from the Earth, from the sun.
Now the ping should be there. It's not there. Wait a little, wait a little, wait a little, wait a little.
Am I really stupid in expecting that this signal is coming?
And then, bang, here we are. So the spacecraft is awake. Bing, here it is again, ready for the mission now.
This is the year of all the action.
It's time to get Rosetta up close and personal with this comet. Today, a key maneuver. Mission manager Fred Janssen has flown in.
In the past, we've had problems with these maneuvers of this size. I'm very nervous. I mean, we need this to go right.
Rosetta is moving fast. She's caught up, but risks overtaking her target. She needs to get in sync. Over the next 12 hours, this team programs the spacecraft to slam on the brakes.
Currently, we're moving at 700 meters per second. We'll be reducing that by approximately 300 meters per second.
A series of zigzag maneuvers, precise turns and angles, all designed to get her close.
If we don't do these maneuvers, then we fly past it at 50,000 kilometers at a high speed. And that was it. Goodbye, Gracie.
What they've programmed will take hours. Andrea is eager to see the results.
We were very anxious to see how the spacecraft would react last night. Andata bene, sì, no. Guarda qua le pressioni.
It worked. Confidence gained. Comet 67P is within reach.
Welcome to the most important chapter in the life of Rosetta.
go to the MCR to live the last crucial moments with my people.
Sylvain, say the famous words, please.
We're at the Comet. Yes!
This is groundbreaking. It's just, I've become speechless at trying to describe what we're going through at the moment.
We made it, finally. You can't believe it. It looks like, are we really part of this thing?
Is it real? Are we there? We are looking forward to the image with the highest detail we've ever seen.
From imagery, I can confirm we arrived.
The shape of this surface, to me, looks like something that is continuously changing. These are new, fresh. The activity shapes the surface. It's not a planet, yeah? This thing is something lively.
Lively and unpredictable. With this victory, another hurdle lies ahead. The spotlight now turns to Stefan Ulemak, the man responsible for putting a lander on this comet.
We've seen flatter areas, we've seen very rough areas. It will be very, very challenging to find a good and smooth landing area. But that's part of the fun of the game, isn't it?
Coming up, a game riskier than anyone anticipated.
Cliffs of 100 meters.
It's like all of the comets you've ever wanted to go to wrapped into one. We've made history today.
They've landed on a comet, and incredible, never-before-seen images have started streaming back to Earth. I'm Dan Riskin, and this is a model of 67P. Now, when Rosetta first launched 10 years ago, this was just a dot in the sky. But now that they're close up, they can see that 67P is so much more than the simple snowball they were imagining.
Comet 67P, Churyumov-Gerasimenko.
Churyumov-Gerasimenko.
Gerasimenko.
Churyumov-Gerasimenko.
Churyumov-Gerasimenko, the target comet for Rosetta, is perfect in that it's periodic. We have some idea of how it's orbiting the sun. Therefore, it's predictable, and that has allowed us to plan this mission.
Now, the fascinating thing about this comet is it hasn't always been quite so close to the sun. In 1959, it had an interaction with Jupiter, and the gravity of Jupiter moved the comet closer to the sun than it used to be. This comet hasn't been evaporated and sublimated and burned by the sun, and that means there's a better chance of finding primitive material inside that comet.
This is Comet 67P in the highest detail we've ever seen any comet before.
Flat areas, smooth areas, cliffs of 100 meters size or so.
Here at the Max Planck Institute in Göttingen, Germany, Holger Sirks and his team are taking a closer look. Groundbreaking images arriving daily.
Here the cliff.
This is round?
This is round. This is round, and it's a depression.
Okay.
Holger's team investigates every detail. From these images, resident sculptor Martin Heinrich creates a realistic model with accurate color and texture.
Hi, hallo.
Hallo.
Na, wie sieht's aus?
Ich habe da schon mal so eine Probe gemacht hier.
In our images, it always comes out bright, but it's only bright because we expose so long. It's really pitch black. It's dark like charcoal.
Being able to see and feel slopes gives them a sense of possible landing sites.
We want to have a three-dimensional model just to see topography, the local landscape. So this is really so spectacular.
Crashing through the solar system, this is a moving target. A mountain-sized duck-shaped iceberg on the loose.
This is a very exciting comet, and actually, considering its shape, it's maybe too exciting.
And we are now in there, in the middle of a harsh environment, and gas flowing out and dust moving away.
It will have gas coming off, so it's going to be losing mass. And of course, mass is one of the most important parameters when it comes to gravity and staying in orbit. So if you have something that's losing mass, staying in orbit becomes a problem.
There's a concern that the comet, because it seems like it's connected, its two two snowballs connected and might separate into two parts.
A daunting thought for the lander team.
This would jeopardize the lander. The comet is really the big uncertain in this mission.
Alive and changing as it nears the sun.
We look at carbon monoxide, ammonia,
Sam Gulkis is keeping a close eye on this ice-breathing dragon.
What we're observing here is the gas coming off the nucleus and rushing toward us.
That has included water, which they can compare to the water we have on Earth.
Looks like we're now moving into a new phase.
The whole Moreau team is very excited. Detecting water in the coma was a eureka moment. The reason we want to measure it is the water tells us something about the evolution of the comet.
So the rate at which it's escaping is about 2 of these per second.
We want to study comets because not very many people realize that billions of years ago, there were billions of comets that were hitting Earth, which was dry at that time, and many scientists agree that the water that we're drinking today came from comets. We want to verify this.
If all the water on the Earth came from comets, let's just suppose, you would need 100 million comets the size of 67P. So studying one comet on its own isn't going to tell us the definitive answer to this question, but it's going to really provide a basis for understanding other comets which we'll never visit.
But maybe even more came from comets than just water. Maybe the initial ingredients for life.
By investigating individual dust grains, dust particles, we get a real clue about the very raw material that makes up planets.
This is not dust as you have on the top of the TV. It's dust that is the outer skin of the comet. It contains these compounds that we're interested to look into. By looking at the dust itself, we also get an idea of how the comet evolves, how the coma evolves. It's not just the surface that's emitting gas. Even these lumps and possible snowballs of the comet will evolve dynamically as they leave the comet's surface.
On the Earth today, we can't see that stuff. It's all been buried and processed. There's no ancient material on the planet Earth.
These organic molecules are the building blocks for amino acids, which are the building blocks for life on Earth. So these primordial molecules are considered to be the early stages of where life could have come from.
You see a lot of detail coming out by the shadows, a lot of boulders. These boulders, they are house size. Whatever they are made of, we'll find out.
It was exciting, now it's even more exciting. It's like all of the comets you've ever wanted to go to wrapped into one. So it was a good choice.
How do you feel right now?
I just can't believe it. I just can't believe it. Absolutely. I mean, I'm super moved, and everybody there was crying. It's a fantastic moment. I really started believing it when I saw the picture of Osiris that showed the lander. It was too beautiful to fail. Of course, now that we have a lot of things to analyze, it will not be easy, but telemetry keeps coming, so the lander is alive on the surface. It's history. Yeah, it's fascinating.
It really is. Congratulations.
Yeah, thank you.
So happy for you. Way to go. They got there, but how?
We can't underestimate how amazing it is.
The ingenious design of a dynamic duo.
This was worth it.
You are witnessing the pure elation of the first ever landing on a comet. I'm Dan Riskin. This is the stage where things have been unfolding here in Germany during the landing. And this is a replica of the Philae lander to its actual size. Now, in the hours before separation, all the attention went right here. It's called a cold thruster, and this is designed to send a jet upwards during the landing so that as it presses into the surface, it can get a secure hold. Now, when they sent a message to this, it didn't respond, and that got a lot of people pretty nervous. But it's just one piece out of a whole system. How do you design a dynamic duo for a mission this extreme? Building a spacecraft is rocket science.
Challenging, very challenging. It's one of the most difficult things you can try.
What we had to do is miniaturize the laboratories we have on the Earth, make them tiny, compact, low power.
Their idea? Send a probe to catch a comet and put a lander on its surface.
For me, it's the sexiest mission that exists to date. The Rosetta mission has 3 unique goals: the rendezvous, the escort, and the cherry on the top, is really the landing.
Designed with giant solar wings, this spacecraft has traveled further than any other using only the sun for power.
Talking about distances from the sun of about 800 million kilometers. This is more than 5 times the distance between the Earth and the sun.
The van-sized orbiter launched 10 years ago. Packed inside, the potential to rewrite all that is known about comets.
The payload on Rosetta is a full suite of scientific instruments, ranging from remote sensing instruments, cameras, to things that are sampling in situ. They're taking dust measurements and the gas, and also the plasma that is the environment around the comet.
Now closer than ever, cameras, some as pricey as $500,000, beam the most impressive images we've ever seen of a comet.
This is the real eye of Rosetta. It's a CCD sensor. As you carry in your camera, this is really pioneering work done some 15 years ago. It's just amazing quality. This was worth it.
Built to handle reckless speeds and even deflect debris around an ever-changing environment.
We would not want to be hit by something relatively large coming off. But the instruments have doors that can open and close.
Everything you do in Rosetta is new. How to fly it, how to operate it, the hibernation, the flying in a strange environment like a comet. This is what makes it absolutely fantastic for us.
For all that the Rosetta orbiter can do, it's the lander that will steal the glory.
Deploying a lander on the surface of the comet is one of the key items of relevance and importance. Getting up close and personal to the comet.
Stefan Ulemak and his team from the German Space Agency have been working on this washing machine-sized lander for 2 decades. Built not only to scratch the surface, but also to dive deep, seeking answers locked in the comet's core.
Philae, the lander, will go down to the nucleus, to the pristine material, and have the chance to measure and analyze the material from the beginning of the solar system.
The day of separation will be tense.
There are 2 buttons. There is a main mechanism and an emergency mechanism. We fire both at the same time, praying that one of them will work.
The lander will drop into an active coma from nearly double the altitude of a cruising 747. Once ejected, it can't be steered. A dramatic descent. Pulled only by the weak gravity of the comet, the fall will take 7 hours.
Depending on the conditions, it's going to be quite a long journey for Philae.
The gravity of the comet is so weak that we actually will have to actively stick to the surface.
In a perfect situation, the lander will land on 3 feet, the ice screws will be deployed, and harpoons will be deployed as well to really fix onto the comet's surface.
But what it fixes to is the big question.
A cometary surface is made of ice and dust. But whether it's very soft material, soft as new fallen snow or cigarette ashes, or whether it's rather hard, like porous ice with dust in there, indeed, this is not clear.
Stefan's team has prepared for just about anything. But they're still guessing and testing. They've brought different surfaces into the lab to see how their harpoons perform.
The test helps us insofar as we learned how the harpoon is penetrating through this soft material. It was slightly deviated and it hit here the wooden box. The tilted harpoon will anchor even better in the material.
All of these components designed to do what no other spacecraft has ever done before.
So this is really a first-timer for all of us.
At the end of the day, what counts is that you do good new science and that you learn many things about a comet and what it means in the universe.
The biggest controversy is when scientists talk to engineers.
He is the worst in that respect.
You're
insisting to keep it.
It's a tough room.
I want to make this all work for everyone.
And we're inside as the battle over where to land gets tense.
So there is no O1, so don't discuss no one.
Arriving from all over the world, the team responsible for this mission has come to Toulouse, France, to select a landing site.
Good morning, everybody. Welcome for this very important meeting.
The challenge? Land where it's safest or go where the science is, even if it's risky. They have to drop this lander on a moving target, and even though they've designed it to stick to anything, the surface might not be what they're expecting. Each person here has their pick.
This is a very cool view I like really a lot. This is a runway, so all we miss is the flashing lights.
Holger Sierks brings new evidence as his team takes the list of 10 down to 5.
So we can provide images and topography and shape. So we have features, cliffs, so we have topography there. These are the pebbles, the boulders, and very large, smooth terrain.
For each site, they look for surface hazards, dangers lurking. They also consider sunlight for power and for imagery.
Scientifically, it's very, very interesting, but it's for you, for the landing team, and it will be hard to find the proper landing site.
It's a fantastic landscape. Yeah, thanks again. I think we all have to digest these wonderful images.
Well, the landing site selection process is not easy.
For me, what's become very frustrating is every week we're talking about the same thing.
Yeah, the gravity must be very low.
Yeah. What is very important is to focus on landing sites that do have a value, do have a real potential.
I want to try and make this all work for everyone. Yeah.
There's been a number of discussions over coffee, at least, with the balance between 100% successful landing and very minimal science to maximizing science and having a little chance of actually landing.
The biggest controversy is when scientists talk to engineers. Engineers are interested in safe landings. On the other hand, scientists want to be in the most exciting place, but it's always very difficult to land on. How do you reconcile these competing interests?
Of course, the top requirement, I think everybody agrees, is to bring the lander down safely, and I think nobody will seriously question this.
There is a lot of instruments that require to be long-standing on the Comet to see how it behaves.
Jean-Pierre speaks for many of the scientists here. He'd like to see a mix of sites on both lobes.
If I am to go on the upper lobe, I would prefer J and D. I don't like the boulders. The boulders tell me big reprocessing. I would like to go as pristine as possible.
I would eliminate G and keep A and C.
But of course, as I said, RFC, we cannot measure because we cannot tune.
Yeah.
Simply landing won't be enough for Wlodek Kaufman. His experiment Concert has the potential to make history. With parts on both the orbiter and lander on either side of the comet, they can scan the nucleus like an ultrasound, seeing inside for the first time ever. This makes him a kingpin at the table.
Okay, go ahead.
Side A, the tuning is very narrow, and we should analyze more, you know.
So, A is bad, but not tragic.
Yeah, perhaps tragic, but
okay,
I don't know.
Yeah.
I don't know.
Concert's important because it's the only measurement that will give us this fundamental leap forward in understanding what the inside of the nucleus is like.
We have to trade, we have to make compromises. I think people will mainly digest what we have discussed today. There was a huge flow of information.
So yeah, it's constant work now. It's 100% 24/7.
There are so many competing attitudes, competing science programs, and it all has to come to a decision very quickly.
A list of 5 is near, but there is continued debate about keeping one site, B, on the table.
We will not disregard B as the safest landing site. B is kind of our safety anchor, I would call it. But there is significant drawbacks from a science point of view.
For the actual properties of the material you want to have access to, B is the worst in that respect.
Yeah.
You're insisting to keep it.
I acknowledge the disadvantages. I prefer to land and have a first science sequence as compared to not land at a very exciting site. Time for a coffee break, right? Okay.
We're making history here. This is the first time this has been done, and there's a lot of stress in the room because of that.
After 2 tense days, there's finally a decision.
We are confident that based on the information we got, we've done the right choice in the 5 sites.
The 5 landscapes couldn't be more different. 3 on the head, 2 on the body, all with substantial rewards and risks.
We're very excited with the potential spots to land. This is such a difficult mission. I have a slightly different look at it. I am excited about any spot to land.
I feel like we've achieved something, but it just means on to the next task.
The next task is up to Andrea and the flight team. They need to find out if they can even drop the lander on each of these 5 sites.
It's a bit of pity we cannot land in landing site A. The analysis we are conducting for these landing sites are extremely demanding.
The team works at finding the best flight path for each site.
Of course, we found some surprises. Some of them were not totally feasible as we expected or as we hoped for, so we had to exclude some of them.
A much higher phase angle. And
some of the sites dropped out quite quickly because from a lander safety point of view, there was a 50-50 chance. The roughness of the surface will have a great impact on the capability of getting the lander safely to the surface.
Back in Toulouse, they've returned to make the choice. Mission manager Fred Janssen is here.
I make the ultimate recommendation on yes, this is the one we go for.
Well, how much favorable is C in terms of energy or power available with regards to J?
If you go for C, we are out. That's all.
It was analyzed, and I mentioned clearly yesterday, that it has the potential to lead to spacecraft and thus lander loss as well. So there is no O1 for C. There only is an O2. So don't discuss an O1. You can never make everybody happy. And it's about trade-offs, about risk all the time. Today, we'd like to tell you about where to land.
Good morning, everybody. I'm very pleased to be able to announce the landing site here today.
The choice is Site J. Reachable for the lander, and with untouched zones, there's a good chance they'll find the pristine material they're after. Nearby jets could be very exciting and dangerous. Site C stands by as backup, less sunlight, and a nerve-wracking approach for the landing team, thanks to a rocky landscape with dangerous cliffs.
We're constantly trading off, how can I put it, the less risky landing site versus the maximum science, and that's always a problem in space.
All right, I'm with Fred Janssen, the mission manager. Now, you ultimately had to make the call that the landing site J is where you wanted to go. Now that you're there, what do you think of that decision?
It's been a good one because we managed. It was the right spot because it all succeeded. And what it scientifically brings, of course, we have to wait. But for the time being, I'm more than content.
And so what is going to happen on J over the coming months? What do you expect from that site? What are you going to learn there?
Well, what we hope to learn is to connect what we measure in the orbiter with what we measure on ground. Because if you don't make the connection, you will never know whether what you measure in space is really the same thing.
All right. Well, congratulations on a successful landing. And now lots of science to be done.
Definitely.
Great. Coming up, anything could happen.
There could be dramatic events.
It's going to be quite a long journey.
Feeling will die at some point.
The excitement will be fantastic.
This is an international mission, and the world is watching.
It's just this worldwide group of people that work together to get this done, and that's how it works. We work together on this mission, and we've made it.
But even though the landing made history, this mission is way bigger than that. I'm Dan Riskin. I'm here in Germany at the European Space Operations Center. The lander Philae and its orbiter Rosetta are holding on for what's going to be the craziest ride in the solar system. The ambitious journey to land on a comet is now a mission to survive with it.
For me, the mission really begins.
The lander, now hooked onto the surface, is about to experience the ride of its life.
We hope it'll be quite quiet. If it's too violent, we won't be able to do what we need to do.
The goal? Dig in, grab a hold, and get primary science done within hours of touchdown.
But the best case scenario is we have a good landing, the anchoring works, we can do all our experiments.
A frenzy of science will begin. Images of the surface will be taken with resolution 100 times finer than a strand of hair. We'll learn the temperature on and below the surface. And the lander, together with the orbiter, will help us see deep inside the comet thanks to radio pulses.
Of course, if Philae survives from November till the March timeframe, we are all very, very happy.
Even if lander systems shut down on the journey to the sun, Philae should stay tethered to the comet. They'll hurtle into the inner solar system with the orbiter above at over 65,000 kilometers an hour. That's 10 miles a second.
The excitement will be fantastic. We will be closest approach to the sun, perihelion, and the activity of the comet will be unbelievable.
It's a 9-month trip, equivalent to the distance between the Earth and Jupiter.
Gas streaming out and dust clouds and jets everywhere. This is going to be the fantastic moment of this mission.
Philae will certainly die before perihelion.
If they lose contact with the lander, the flight team will be even more focused on keeping the orbiter alongside 67P, especially in extreme circumstances.
There could be dramatic events happening, like a gigantic jet or the comet breaking up.
That's hugely challenging to operate in such a potentially violent environment. The scientists are going to be working for years on this, trying to tease out the clues. We know the world is watching this mission. It could revolutionize everything.
All right, I'm with Mark McCaughrean, one of the lead scientists on this entire project. Tell me about that landing and how you think it went.
It went fantastically well. You know, it was even better than a bus arriving on time, 2 minutes after the nominal time. So it was fantastic there. We had to wait a little bit to get confirmation that we were locked to the surface. We had that, but we're not really still quite 100% sure what happened at that point. We're on the comet, there's no doubt about that. We may have hopped, and a hop on an object with so little gravity actually could be quite a long hop before it comes down again. We're on the surface. We're investigating the surface. We have a lot of science data already coming in, but we're trying to diagnose exactly what happened during that first phase.
Now, in the coming months, is that lander still going to be holding on the way you wanted it to, or does it need a tighter grip?
The reason for grabbing hold was all about seizing the moment when you landed, right? We had to arrest that momentum and grab a hold, but we could have let go at that point. Once there is enough gravity, it's very little, but there's enough gravity to stay stuck on the surface. Nothing's going to lift us off. Maybe when the comet gets really active later on, it could, but at the moment, if it's on, it's on. It's not going to go anywhere.
And let's talk about later on. So right now, this is a cold, icy snowball, but it's headed for the sun. So what's that experience going to be like for this little lander?
Well, you know, if we're not locked to the surface, it could experience some winds, some of this outflowing material. What we see at the moment is up to 5 kilos of water coming off per second. That could increase by a factor of 100, and that's going to be over the whole surface. Tons of water up to per second. And, you know, if Philae's landed on a place which becomes active, it might fly off. We think we've landed somewhere very safe, very flat. We've got some images which we're trying to piece together exactly where we are. We're not on the edge of a boulder. We're not in the middle of a crevasse field. It looks nice, but it could be an area that becomes active. We just don't know at this point.
And so what's next for you? What are you looking forward to in the coming little while?
Well, the main battery only lasts 64 hours, and we burn some of that going down to the ground, down to the surface. So we're running all the experiments as quickly as possible. They're running. We're not in contact at the moment with Philae because Rosetta's over the horizon, but science is going on. Tomorrow we'll link back up, get some more data back. We've got good stuff already, but we hope that the secondary battery will then charge. We'll be able to then continue the science, and there are some great bits of science we won't even do until a few weeks downstream.
Well, congrats on a great landing.
Thank you very much.
You got it there.
Hugely exciting day. Thanks very much, Dan.
It is an exciting day. Lots to come from this lander, and it's inspiring a lot of other projects as well. Coming up, if you're in awe of this mission, imagine what else we're about to grab a hold of.
It's the most hazardous asteroid in the solar system.
Images like this are grabbing us and taking us to a place we've never been. This is really historic. We've put a spacecraft on the surface of a comet. And while the Rosetta mission extends our reach into space, there are already other teams looking to take that reach even further. This might be the future. Catching and exploring wandering cosmic bodies.
All right.
Space dreamers are fighting for the chance to get close, grab a hold, and bring souvenirs back to Earth.
There's a sci-fi aspect to it, definitely. Is the Earth endangered by being hit by a big comet or an asteroid?
3, 2, 1. First up, a little lander ready to scout an asteroid. Hayabusa 2 from the Japanese Space Agency is gearing up to send this mascot to tumble around and get a sample.
The key aspect of mascot is that it has an internal mobility system, meaning it can move across the surface of the asteroid, like a dice which rolls itself.
Rolling not too far behind, OSIRIS-REx, a NASA mission well on its way to Bennu, an asteroid that could come a little too close.
It's one of the most potentially hazardous asteroids in the solar system. We don't want to go to a pebble. We don't want to go to a small boulder. We want to go to a mountain to understand its geology and its history, ultimately to send the spacecraft to the surface, get a sample, and bring it back to Earth.
While those missions are locked for launch, NASA is thinking even bigger. They're spending millions on concepts designed to bring an asteroid a little closer, or at least a piece of one.
Oh, this is slightly too fast.
For that, drills are a no-brainer.
We love drills. We focus on extraterrestrial drilling.
Honeybee Robotics is combining their drills with this robotic arm to bring back boulders.
The trick is to be able to pull it off the asteroid without breaking it. Let's use the excavation tool now to get a cavity underneath that boulder.
They're experts at drilling on Earth, but can they pull it off in space?
It's very exciting. We can do this. We just need a little bit of practice.
Practice is exactly what Aaron Parnas and his team from JPL are getting with their spiny-legged rock crawler, the Microgripper.
When I tell people I'm building a gripper to bring an asteroid back, you get a lot of questions. Oh yeah? You want me to load it up?
Yeah, go for it.
That's gripped. It has lots of sharp hooks that grab onto the surface of a boulder. Any one of them probably can't hold much, but if you can get tens or hundreds of them to work together, all of a sudden you can lift a giant boulder.
Airborne Systems in California is going even bigger than that.
It's a very audacious objective to totally envelop an asteroid. We're going to lower the simulated asteroid down. Now we're going to clasp the air beams around the asteroid and then move the full asteroid to another orbit. It's a pie-in-the-sky kind of a mission.
Capturing an asteroid and putting it where you want it, that's the kind of big thinking NASA is after. They're lining up missions within the next decade to keep a firm grip on what's lurking in space. Big thinking is what landed this team on a comet today. You know, in our lifetime, there will only be a few moments like this. And what a thrill to be here at the European Space Agency for this giant leap forward in space exploration. I'm Dan Riskin. Thanks so much for joining us on this epic journey.
I can't begin to explain the emotions that there are people in there that worked their lives on this mission, and we did it. We were actually seeing telemetry coming back off of the surface of the comet. That's just mind-blowing.
Oh man, it's unbelievable. This has cost me a year of my life, but it's worth it.
It was too beautiful to fail. There it was the moment where I thought it's gonna really work.